Spring 1942. Deep inside a German weapons lab, a team chases a bizarre idea, not for the battlefield, but for anti-aircraft tests. A year later, that same concept becomes Hitler's obsession, and by his command, it is forced onto the war's most vulnerable tanks. This is the true story behind Germany's infamous corner-shooting rifle, a miracle weapon that was doomed from the start. What really happened after the Führer's order set this disaster in motion? Colonel Hans Joachim Schade, working inside the labyrinth of Rheinmetall-Borsig's research division, faced a problem that had nothing to do with the trenches or city streets. The original challenge was simple on paper: how to proof test anti-aircraft barrels safely without putting technicians in the line of fire. In March 1942, a memo landed on Schade's desk, outlining the need for a firing solution that could redirect the bullet's path, essentially to shoot around a corner, but only for laboratory safety. No one imagined this would ever reach the battlefield. The first experiments looked more like a physics demonstration than weapons development. Schade's team took a 20mm anti-aircraft barrel, a thick curved steel tube, and tried to use it as a trough for standard 8mm rifle bullets. The expectation was universal. The bullet would grind to a halt, friction would ruin the experiment, and the idea would die in the lab. But on April 15, 1943, test logs recorded something nobody predicted. The tighter the fit between bullet and barrel, the better the bullet traveled. Instead of jamming, the 8mm rounds slid through the curve with surprising consistency, even with just a tiny 0.2mm clearance. The engineers, trained to trust calculations over hope, were stunned. The supposed friction nightmare had turned into a technical breakthrough. Schade documented the results. Not only did the bullet survive the curve, but accuracy, at least on the test bench, was better than anyone dared expect. The team bored the first centimeter of the barrel slightly wider, up to 9 or 10mm, to help the bullet recenter after being yanked between different rifling directions. Early skepticism gave way to cautious optimism. If a bullet could be forced to change direction inside a steel pipe, maybe it could be done on a weapon, too. What started as a safety measure for anti-aircraft guns now looked like a possible answer to problems far beyond the test range. The success of the so-called massive trough experiment opened the door to new applications. It also set a dangerous precedent. If the lab could make it work, someone on the front lines would want to try it under fire. The question was no longer whether the concept was possible, but how and where it would be used next. At Kursk in July 1943, the battlefield became a proving ground for German armor and for its most glaring weaknesses. 91 Ferdinand tank destroyers rolled into combat, each one boasting the most powerful 88mm anti-tank gun in the Wehrmacht's arsenal. They could destroy Soviet tanks from over 3 kilometers away. But as the fighting closed in, their greatest strength turned into a fatal liability. Not a single Ferdinand carried a machine gun. Soviet infantry, armed with Molotov cocktails and explosives, slipped through the chaos and attacked at point-blank range. Reports from the front described crews trapped inside their steel fortresses, powerless to defend themselves as flames and smoke poured through open hatches. Tracks disabled by mines or artillery left dozens of Ferdinands stranded, easy prey for determined soldiers with nothing but a bottle and a match. By the end of the first day, only a dozen remained operational. The rest littered the steppe, some burned out, others abandoned, all silent witnesses to a design oversight that cost lives. Word of the debacle traveled quickly. The panic among tank crews and the humiliation of seeing invincible vehicles destroyed by foot soldiers reached the highest levels of command. Hitler, always eager for technical solutions to battlefield disasters, seized on the idea of a curved barrel firing device. The concept, now freed from its laboratory origins, became a matter of personal interest for the Führer himself. According to secondary accounts, He demanded a demonstration at Rastenburg, his headquarters in East Prussia, in June 1943. Engineers assembled prototypes, and the spectacle unfolded for the Reich's top brass. Whether or not the demonstration impressed the generals is lost to history, but Hitler's reaction was immediate and decisive. He issued a direct order: accelerate the development of a curved barrel weapon for both tanks and infantry. The project, once a technical curiosity, now carried the weight of the Führer's will. Resources diverted overnight. Factories like Rheinmetall-Borsig received new priorities. Zeiss, the optics giant, was tasked with producing specialized periscope sights for the weapon. The Armaments Ministry began drawing up plans for mass production, even as the technical challenges piled up. No one dared question the wisdom of the order. In the culture of the Third Reich, the leader's enthusiasm overruled the doubts of engineers and the lessons of the battlefield. The Krummlauf curved barrel system was no longer just an experiment, it was a mandate. The pressure to deliver a miracle weapon pushed the project from cautious optimism into a full-scale arms race against time, physics, and reality itself. Engineers pressed ahead with the Krummlauf, confident that their technical wizardry could overcome the violence of a bullet forced to change direction mid-flight. The first centimeter of the barrel was bored out to 9.6 millimeters, just enough space for the 8 millimeter bullet to recenter after being yanked between two sets of rifling. The idea was elegant: a chamber that would catch the projectile as it left one groove, guide it smoothly into the next, and preserve accuracy despite the curve. May 1944 design notes describe this as a sophisticated solution, the kind of detail that made German engineering famous. Real world had other plans. In April 1945, captured Krummlauf barrels arrived at Aberdeen Proving Ground, where Colonel Quinn and his team ran a series of live-fire tests. The first shots revealed a problem no one in Berlin had anticipated. Each bullet, hammered through the curve, fractured at the cannelure, the small groove where the case crimped the projectile. Instead of a single slug, the round burst apart, spraying fragments in a cone barely 3 meters wide. What was meant to be a precision rifle had become a close-range shotgun, its lethality dropping off almost immediately beyond the muzzle. Fragments from hay bale targets told the story in metal and splinters. Quinn's report noted, all bullets test-fired were seriously distorted. The recentering chamber, for all its cleverness, could not prevent the bullet from breaking under the strain. The intended accuracy dissolved into chaos. At short distances, the weapon could pepper a target with shards, but at any range, control was lost. Ingenious feature had turned into its greatest liability. The very effort to preserve accuracy destroyed the bullet's integrity. For frontline soldiers, this meant a weapon that was unpredictable at best, dangerous at worst. The laboratory marvel had failed its first real test. Engineers scrambled for answers, searching for a way to relieve the pressure inside the barrel. Their next attempt would open a new set of problems. Engineers tried to solve the bullet fragmentation crisis by drilling a line of half-millimeter relief vents along the curve of the Krummlauf barrel. On paper, these tiny holes were supposed to bleed off excess gas pressure, sparing both the barrel and the bullet from catastrophic stress. But the solution created a new threat just inches from the shooter's eye. Each shot sent a blast of hot gas and burning powder straight into the periscope optics. Test logs from May 1945 describe the sight picture fogging over in seconds, the mirror clouded by residue and heat. Firing more than a few rounds in a row left the shooter looking into a wall of steam and grit. The only fix was a crude triangle of sheet metal, hastily riveted in place to shield the optics. Even then, the view through the periscope was never clear for long. Every improvement to the barrel brought a new hazard for the operator. The real disaster, though, began when testers pulled the trigger in rapid succession. At Aberdeen Proving Ground, Colonel Quinn watched as American soldiers fired bursts from a captured Krummlauf. The weapon didn't just kick back, it twisted violently in the shooter's hands. After 3 shots, the combined force of normal recoil and the sideways torque from the curved barrel spun the entire rifle nearly 88 degrees. One soldier nearly lost his grip as the gun wrenched sideways, threatening to pull him off balance. The test report from April 20th, 1945, recorded the phenomenon in blunt terms. Shooter and weapon rotated approximately 90 degrees after 3 rounds. Sustained fire was impossible. The rifle became a danger to anyone using it, the recoil and torque working together to rip the stock from the shooter's shoulder. Every attempt to tame the forces inside the barrel only amplified the chaos outside it. The Krummlauf had crossed a line, no longer just unreliable, but actively dangerous. By the end of the spring tests, even the most optimistic engineers had run out of explanations. Colonel Quinn summed it up best. The strain on the barrel is great, and it is believed that it would enlarge, erode, and pocket. The Krummlauf wasn't just failing, it was defeating itself, one shot at a time. The curved barrel rifle wasn't just a German experiment. After the war, American engineers at Aberdeen Proving Ground built their own version, adapting the M3 grease gun with a sharply bent barrel. The goal was the same: let tank crews fire at close-range threats without exposing themselves. But every test ended in disappointment. The .45 caliber bullets, forced through a steel curve, shattered or veered off target. U.S. Ordnance reports from October 1945 noted rapid barrel wear, severe inaccuracy, and a lifespan so short that the project was dropped before it left the prototype stage. On the other side of the world, Soviet designers tried to solve the same problem. In December 1944, a Soviet technical memo described experiments with a curved barrel attached to the PPSH-41 submachine gun. The outcome was nearly identical. Bullets broke apart, barrels eroded after a handful of rounds, and accuracy vanished beyond a few meters. The unnamed Soviet engineer behind the project abandoned the design, recording in his notes that the forces inside the curve made reliable shooting impossible. Neither superpower found a way to beat the laws of physics. The American and Soviet copies failed for the same reasons as the German original. Bullets couldn't survive the turn, and barrels were ruined in a matter of minutes. With every attempt, the promise of a corner shooting weapon collapsed under the same relentless stresses. No amount of engineering could stretch its lifespan beyond a few hundred rounds, setting the stage for the harsh reality of the Krummlauf's own 300-round death sentence. Barrel after barrel landed on the test bench at Aberdeen, each one more battered than the last. The 30-degree infantry Krummlauf, designed for the STG-44, barely survived 300 rounds before the steel in the curve eroded and fractured. The 45-degree version fared even worse, failing at just 160 rounds. Tank-mounted 90-degree barrels, never officially tallied, but examined by U.S. Ordnance, likely lasted fewer than 100 shots before the metal warped beyond use. Standard rifle barrels of the era were expected to endure 5,000 to 20,000 rounds. The Krummlauf was disposable by design, an engineering admission that the weapon was never meant to last. Production records from January 1945 show the scale of this gamble. Rheinmetall-Borsig delivered 500 tank mounts. Zeiss, the optical powerhouse, manufactured 1,500 periscope sights, all intended for a weapon system that self-destructed faster than any frontline rifle. A Zeiss manager, whose name is lost to the archives, signed off on the final delivery, noting in a surviving memo the urgency of the program, a phrase that now reads like a quiet confession of futility. Plans called for every STG-44 infantryman to receive a Krummlauf, but the war ended before mass distribution could begin. Warehouses filled with unused sights and mounts as the front collapsed. Steel and labor poured into a device that was obsolete the moment it left the factory. In the final months of the war, Germany's most advanced engineering firms were locked in a race against time, physics, and defeat, producing weapons destined for the scrap heap before they ever reached the battlefield. In 2003, a patent filed under US 6,896,247 described a weapon that could finally shoot around corners without forcing bullets through a tortured steel curve. The inventor, Amos Golan, a former officer in Israel's Special Forces, had studied the lessons of failed wartime engineering. Instead of bending the barrel, Golan's design hinged the entire front end of the gun, allowing the operator to remain safely behind cover while aiming through a digital camera and periscope sight. The system, known as corner shot, entered service with police and military units in 2004. Its mechanism let the shooter pivot the weapon left or right, fire standard ammunition, and see the target on a small screen, solving the core problems that doomed the Krummlauf. Corner shot's lineage is unmistakable. The tactical need, delivering firepower from behind cover, remained unchanged from the trenches of World War II to the alleys of the 21st century. But the solution abandoned brute force in favor of mechanical simplicity and digital precision. Modern remote weapon stations on armored vehicles, too, echo the same principle. Keep the operator protected. Let the machine take the risk. The Krummlauf's legacy endures not as a triumph of design, but as a cautionary tale that shaped future innovation. Where physics defeated desperation, ingenuity found another route. Military innovation still walks a knife edge between genius and folly. Billions are spent each year chasing battlefield breakthroughs, yet physics, not ambition, sets the limits. As nations race to field the next game changer, the lesson endures. Technical brilliance can't override reality. Even today, engineering hubris risks repeating the past. The line between invention and fiasco remains as thin and as costly as ever. What's your verdict? Let's discuss below.